I'm Balázs from the University of Sussex, and I'm going to present my work, which was done with my supervisors, Thomas and Jamie. And I'm also going to talk about delay. So at this point, maybe you don't need any more motivation, but I will give you some anyways. So I think it might be interesting from neuroscientists, since experimentalists have shown that myelination, which is an effect on delays, might be a part of learning, but it was also of interest in computational neuroscience almost 20 years ago at this point, but also more recently, delay learning algorithm has been shown to be quite effective in keyword spotting tasks. And this formalism that we're using should be suitable for various neural models, but to make our job a bit easier, we chose a specific neural model, a commonly chosen one, the leaky integrated fire neuron, which consists of three things: the integration, which is that plus I, and then the leak, which is the minus V, and then we have the firing mechanism, which consists of a transition condition. So whenever the membrane potential of the neuron reaches this V, it emits a spike, and then two things happen. We have the membrane potential resets, and there's a jump in all connected neurons, which is as strong as the synaptic strength. And Wunderlich and Pila with the event prop algorithm showed how you can derive the gradients in this formalism for W. And you get these relatively complex equations, but the cool thing about it is that the actual gradient updates only happen at spike times, which makes it quite efficient and suitable for neuromorphics as well. And if we want to introduce synaptic delays into this system, what we need to do is that if we go back again to this leak integrated fire neuron, both the integration and the leak stay the same. The only thing that changes is that whenever we reach this transition condition, the neuron emits a spike, but it emits it, and it doesn't immediately arrive at the connected neurons, but it arrives a given amount of time later, which is the synaptic delay. And just again, here is the event prop weight update. This is what it looks like. So if we introduce synaptic delays between neurons, then the weight updates become this. So it still only happens at spike times, but now we need to be careful that we align emission and arrival times. And here we denoted the delay with D. We can derive the gradients of these Ds as well. And this is what we end up with, which maybe intuitively doesn't say too much, but the cool thing about it is that also only happens at spike times. So first we looked at the yin-yang data set, and we saw something very similar to what Jimmy showed before, namely that delays always help, and especially when the model size decreases, it becomes especially useful. And we looked at spiking Heidelberg digits, where we saw improved performance with fewer parameters than before, but we did not reach state of the art. And the same can be said with spiking speech commands. We improved our performance, we decreased the network size, but we didn't reach state of the art. So I guess you might ask the question, what is the purpose of this? Why wouldn't you use the state of the art method? And that is mostly the efficiency. So here we compared with dilated convolutions, the state of the art delay learning method on these keyword spotting tasks with maximum delay time steps on the x-axis. And you can see that both in terms of GPU memory size and training time, we significantly outperformed it, and we can fit much bigger models into the GPU and train them faster. And that's it. Thank you very much.